As of the 22nd of June 2016, the Door and Hardware Federation trade body that represents the UK gate and door industry has released a new code of practice, DHF TS 011 2016. Several key elements of this code of practice have been designed to demystify complex standards and make things clearer for installers and maintainers of gates and barriers to understand. Chapter 1. Force testing gates and barriers. In the following animations, we will explain in simple terms how to carry out these tests in line with the code of practice. You will require a compatible force testing device to take the measurements, which should be accompanied by a measurement extension arm set. For the purposes of these tests, the code of practice has set the benchmark for acceptable pass values at 90% of the limits described in the standard BS-EN 12453. If the results fall between the 90 to 100% values, then 3 tests are to be taken at each measurement position to calculate the average value, which must fall within the limits. Let's take a look at a typical sliding gate setup. As the sliding gate closes, there are 3 measurements to be taken at 3 different heights, as shown in the animation. For reference, these are 50 mm from the bottom of the gate, 300 mm from the top, up to a height of 2.8 meters, and then the middle point between these 2 measurements. Each of these tests is to be measured with the force testing device using a 500 mm separation from the closing position. Once these tests are complete, the position that produced the highest values, i.e. those closest to the limits described, is to be tested again, at a 50 mm separation distance from the closing position. Assuming all the tests carried out fall within the 90% limit values described, then force testing on the closing crush hazard can now be considered complete. If an opening crush hazard exists at the other end of the gate, these tests are to be repeated there also. If any values exceeded the 90% limit, each test should be repeated 3 times, and the average value calculated for each measurement point. If the average value is still above the 90% threshold limit, it is recommended to assess what could be causing this. For example, if a motor force is too high, a safety edge profile too shallow, or a transmission system latency. Once complete, retest. This applies to all gate and barrier types. The sliding gate full speed impact test assesses the suitability of portal fixed edges. These edges should be of the same type used on the leading closing edge, to ensure safe values are met. Now we can look at a typical swing gate setup. As with the sliding gate scenario, there are again 3 measurements to be taken at 3 different heights. For double leaf swing gates using leaf delay, or for single leaf swing gates, tests should be carried out using method A. For leaves closing parallel to each other, tests should be carried out using method B. Again, assuming all the tests are passed within the 90% limit, the final test at 50 mm separation can be carried out and verified. Now we can see a typical swing gate opening hazard where the flat leaf surface is open within 500 mm of a wall or a fixed object. Swing and folding gate open crush hazards are measured at the most outstanding feature up to 2 meters above the ground, or in the absence of protrusions on either surface, 1 meter out from the hinge, 1 meter up from the ground. If motor slowdown settings have been used to achieve these pass results, an impact test should be carried out at the point the leaf achieves full speed, and at the center measurement height of the gate. The swing gate full speed impact test assesses the suitability of lower rail hazards, such as crush hazards on small gaps, impact hazards on larger gaps, and variable hazards on gaps that can change with motion. The edges used here should be of the same type used on the closing edge to ensure safe values are met. Now we can look at a typical barrier setup. Crushing force measurements are taken 200 mm in from the tip of the boom at a maximum height of 2 meters. With a force impact mass of 400 newtons, a 2 meter extension arm is required. Where an articulated boom offers no vertical resistance at initial contact, for example some chain-connected designs, force time may be ignored provided that the crushing force is within limits. Where a boom with collapsible skirt is used, the skirt may be secured in the collapsed position for the tests, provided that it will collapse without exerting more than 50 newtons. Following completion of these tests on any type of gate, it is recommended to create a report or document presenting the values recorded, along with the location and details of the customer's gate, date and time, and conditions that the tests were carried out under. This information is vital to demonstrate compliance and provides written evidence that the gate was safe on the date of testing. Chapter 2. Defining lower rail crush or impact hazards on swing gates. This area has always been a concern when addressing safety requirements, as the current BSEN standards did not clearly define any parameters. The DHF TS 011-2016 Code of Practice now provides a simple set of terms to define both crushing and impact hazards in this area. Firstly, let's take a look at a swing gate in its opening and closing sweep. The Code of Practice defines that where the gap beneath a swing or bifold gate is constant and above 120 mm, then this can be considered an impact-only risk. Please note, all other hazard areas of the swing gate, the hinges, sweep obstructions, etc., must be assessed separately and designed out or eliminated where possible. The Code of Practice also defines that where the gap beneath a swing or bifold gate is variable, and or below 120 mm, then this can be considered a crushing risk. Again, all other hazard areas of the swing gate must be assessed separately and designed out or eliminated where possible. When addressing these crushing or impact hazards, care should be taken to select an appropriate solution that eliminates or reduces the risk as much as possible. The Code of Practice lists several methods to achieve this, including safe design, application of force limitation through motor technology or safety edges, or elimination of all contact hazards through the use of light curtain devices. In the following animation, the gate leaf has been fitted with lower rail safety edges on either side of the gate to protect the crushing hazard. When implementing this type of solution, the forces exerted by the gate should be measured in line with the force testing requirements laid out in the Code of Practice. Following completion of these tests on any type of gate, remember to create reports or documents presenting the values recorded. Chapter 3. Defining swing and bifold hinge area, crush or shearing hazards. This area has always been a concern when addressing safety requirements, as the current BSEN standards did not clearly define any parameters. The DHF TS 011-2016 Code of Practice now provides some simple guidance regarding this dangerous hazard. Firstly, let's take a look at a swing gate in its opening and closing sweep. Here we can see an example of a reducing hinge gap, and how easily a body part could become crushed in this area. Careful consideration should be taken when assessing this hazard, as multiple crushing points and shearing hazards can be present depending on the design of the gate. The Code of Practice defines that where the hinge gap in a swing or bifold gate varies by more than 20% and or is over 100 mm, then this is considered to be a hazard. Please note, all other hazard areas of the swing gate, the hinges, sweep obstructions and etc. must be assessed separately and designed out or eliminated where possible. The Code of Practice also defines that where the hinge gap in a swing or bifold gate is constant and between 25 mm and 100 mm, then this can be considered safe, remember to note, all other hazard areas of the swing gate must be assessed separately and designed out or eliminated where possible. When addressing these crushing or shearing hazards, care should be taken to select an appropriate solution that eliminates or reduces the risk as much as possible. The Code of Practice lists several methods to achieve this, including safe design, guarding solutions, application of force limitation through safety edges, and light curtain technologies that prevent access to the dangerous gap. In the following animation, the gate leaf has been fitted with hinge safety edges on the inside gaps of the gate to protect the crushing hazard. When implementing this type of solution, the forces exerted by the gate cannot be easily or safely measured with current test equipment. The functionality of these edges should be tested periodically as recommended in the Code of Practice, and they should be connected to the gate control system and monitored as part of the Code of Practice requirements. When using hinge guards that are designed to prevent access to the pivot area of the leaf, they must be durable, resistant, and designed in such a way that they do not cause a hazard to still exist. Please note, all safety solutions including safety edges should be assessed in the same way and address all potential crushing and shearing hazards. When retrofitting these solutions to existing gates, remember to create reports or documents presenting the values recorded. Chapter 4. Performing safety tests in the sliding gate portal area. In the following animations, we will explain in simple terms how to carry out these tests in line with the Code of Practice. Firstly, you will require a compliant test piece as illustrated on screen. This must meet the dimensions specified of 120 by 120 mm in diameter and 500 mm in length. It must also be made of rigid material such as steel or hard polycarbonate. The aim of this test piece is to verify that the safety edges fitted in the portal area are configured in such a way so that they detect any potential draw-in or shearing risks. Let's take a look at a typical sliding gate setup. To verify that the safety edges are correctly placed and are protecting against draw-in and shearing risks, the gate should first be switched safely to manual release mode. Please ensure that it is safe to do so before proceeding. Then insert the portal edge test piece into the gate in one of these three configurations. The first configuration is for gates with wide spacing. Place the test piece as far into the infill as you can, or centered if possible. The second configuration is for narrow spacing. Place the test piece so that it fills as much of the gap as possible. And the final configuration is for a gate infill that is protected by a fine mesh. Place the test piece against the mesh so that it fills as much of the gap as possible. Once in place, carefully push the sliding gate leaf toward the portal edges to ensure the test piece is detected. Ensure that the test piece is detected on both sides of the gate portals. If the test piece fails to activate the safety edges, then this is considered a fail, and further preventative steps must be taken to address this hazard. For example, the edges may need to be moved further in or changed for a different type and depth of profile. Repeat the tests for any further portals or positions relevant on the gate. The sliding gate full speed impact test assesses the suitability of portal fixed edges. These edges should be of the same type used on the leading closing edge, to ensure safe values are met. Following completion of these tests on any type of gate, remember to create reports or documents presenting the values recorded. For more advice on DHF TS 011-2016 Code of Practice, and to stay up to date with the latest in gate automation and safety, please subscribe to our YouTube channel, youtube.com/EasyGates. Like us on Facebook or follow us on Twitter.